So this is the first problem of in-class exercise. The 2 kg sphere is attached to the light rod, which rotates in the horizontal plane centered at O. If the system is subjected to a couple moment of 0.9 t square Newton meter, where t is in seconds, determine the speed of the sphere at the instant t is equal to 5 seconds starting from rest. So in this example, we need to calculate the velocity, the speed of the sphere 5 seconds after the couple moment of 0.9 t square is applied at O. The key word here is starting from rest. That means the sphere is not moving when time t is 0. That means initial momentum, angular momentum of sphere is 0 with respect to O. In order to solve this problem, we need to apply the equation for angular impulse and momentum. So we need to work with this equation. In this equation, the h0 h01 is the initial angular momentum plus sigma integral m dt is the angular impulse and h02 is the final angular momentum. So an HO in this example can be calculated using this equation, which is distance multiplied by mass multiplied by velocity. Okay. So let's apply this equation to our problem. By the way, the ball follows the circular path while the angular momentum is applied. And this is the path that ball follows. And at the given instant, the velocity of the ball is tangent to the path and points in the direction of motion. So let's call this is the position of the ball, which is at t equal to 5 seconds. Then this velocity is v2. This is what we need to determine. Speed of the sphere when t is 5 seconds. So h01 plus sigma integration of 0 to t moment about O dt is equal to h02. Let's label this as equation 1. h01 in this equation is mvd, that is mass multiplied by velocity multiplied by distance. Beginning velocity v1 is 0 because starting from rest, so this number is 0. Final momentum h02 is mv2d. Mass of the ball or sphere is 2 kg. v2 we don't know, but distance from the center of ball to the point O is 0.6 meters. It's given in the problem. So this number is 1.2 times velocity. Now substitute h01 and h02 into equation 1 and integrate given moment of 0.9 t square with respect to time for time equal to 0 to 5 seconds. Now it is 0. So now equation 1 becomes 0 plus integration 0 to 5 seconds 0.9 t square dt is equal to 1.2 times v2. Integration of 0.9 t square is 0.9 t cubed by 3, and we need to substitute t is equal to 5 as the final value minus t is equal to 0 as the initial value is equal to 1.5 times v2. When you solve this equation, you will get v2 is equal to 31.25. And what should be the unit for V2? It is meters per second, because this is the problem in SI system. And that is the full solution for problem number 1. Okay, problem number 2. A 4-pound ball B is traveling around in a circle of radius r1 equal to 3 feet with a speed Vb1 equal to 6 feet per second. If the attached cord is pulled down through the hole with a constant speed Vr is equal to 2 feet per second, determine the ball speed at the instant r2 is equal to 2 feet. How much work has to be done to pull down the cord? Neglect friction and the size of the ball. So if you, in this example, if you imagine the path that is taken by the ball while the string is pulled down, then it's a spiral path. So ball not only rotates on the disc, but it also moves towards the center when the cord is being pulled down. So to solve this problem, we need to use polar coordinates. And the center of the disk is the origin of the coordinate system. Hence, at each point along the path, the velocity of the ball has two components. One is the component which is along angle, which is transverse component of the velocity v theta, and the component which points towards the radius, and it's called the radial component of the velocity vr. However, only at the beginning, while the cord is not being pulled yet, the velocity has only theta component. So this Vb1 is only V theta 1. There is no radial component because the cord is not going towards the center at the beginning. Second point to remember is that we need to apply the equation for conservation of momentum here, because we need to neglect the friction and there is no effect of gravity. So we can say that the momentum of the ball is conserved when it moves from r1 equal to 3 feet to r2 equal to 2 feet. So let's apply the equation for the conservation of momentum. Let's say that the center of the disk is O. So HO1 is the momentum of the ball at this point, which is r1 equal to 3 feet, and HO2 is the momentum of the ball when the distance, when the radius of the cord, length of the cord is 2 feet. So this is at r1 equal to 3 feet, and this is at r2 equal to 2 feet. So as per the equation of momentum is mass multiplied by velocity. Now this velocity is only theta component of the velocity and not the radial component of the velocity, because the linear momentum is because of only the tangential component of the velocity and not radial component of the velocity. So v theta 1 m v theta 1 multiplied by r1, which is distance from the point of rotation. So this is m, v and d, m multiplied by v multiplied by d as per our equation, equal to m v theta 2 multiplied by r2. V theta 1 is same as Vb1, and that's given as 6 feet per second. We don't have to worry about converting mass from pound to slug because it's the same mass on both sides, so this will get cancelled. Now this velocity component we know initially, that is 6 feet per second multiplied by 3 feet is equal to v theta 2 multiplied by 2 feet. So as per this calculation, v theta 2 is 18 divided by 2, so it's 9 feet per second. This is only the tangential component of the velocity when the chord is 2 feet long. So the absolute velocity v2 at that time is v theta 2 square plus vr2 square, because absolute velocity has both theta component and radial component. Now v theta 2 is what we have just calculated, so it's 9 square plus radial component of the velocity when radius is 2 feet is given in the problem. Look at this number, 2 feet per second. This is 2 square. And this answer is 9.21 feet per second. So this is the absolute velocity of the ball when the chord is 2 feet long. This is first part of the problem. For the second part of the problem, we need to calculate how much work is being done in pulling the cord and bringing the ball to 2 feet distance. So now when the cord is being pulled down, it's the kinetic energy of the ball that changes. So we can apply the equation of work and energy to calculate the amount of work done. So initial kinetic energy of the ball, that is 1/2 mv1 square, plus all the work done while moving ball from 1 to 2 is equal to final kinetic energy of the ball, 1/2 mv2 square. So now work done is equal to 1/2 final kinetic energy minus initial kinetic energy. At this point, be careful that the number 4 pound, we need to convert this into slugs by dividing it with 32.2. Initial, and this is the final velocity v2, we have just calculated that number here, which is 9.21. So this is 9.21 square minus 1/2 4 divided by 32.2 multiplied by absolute beginning velocity, which is 6 feet per second square. Okay? And this was given. So when you do this math, you will get the number which is 3.03, and the unit for work done is feet pound. And that's our second answer. That completes the solution. Problem number 3. If the rod of negligible mass is subjected to a couple moment of 30 t square Newton meter, this is the applied couple moment, 30 t square, and the engine of the car supplies traction force of 15 t Newton, this is applied traction force, to the wheels, determine the speed of the car at the instant t is equal to 5 seconds. The car starts from rest. This is useful information. The total mass of the car in rider is 150 kg. Neglect the size of the car. That means consider the car as a particle. So in this example, weight, which is 150 kg, x downward. This is W, which x, let's say, which x downward here. This is the axis of rotation. Since the W is parallel to axis of rotation, there is no movement from W about O. Only two externally applied moments we need to consider in the problem. One of them is 30 t square applied at O directly, and the second one is the moment coming from the force, traction force, 15 t newtons. So this is the force and this is the distance from axis of rotation So this is 15t multiplied by 4 meter, that is the second moment. The car starts motion from rest, so initial angular momentum of car is 0. Then the car is subjected to two couple moments which changes the final momentum of the car, and from that final momentum equation we can calculate the velocity of the car after 5 seconds. So for this problem we need to calculate v2. What is the velocity of the car at t is equal to 5 seconds? So let's write down our equation. So HO1, that is initial angular momentum, plus sum of angular impulse about O is equal to final angular momentum. Now the equation for angular momentum is mass multiplied by velocity multiplied by distance from center of rotation, and that distance d is 4 meters. This is sigma, so it includes summation of both the integrals of moment from 30t square and this 15t Newton. So I will write two terms for the middle part because it is sigma. So first one is, let's say, for the couple moment, so it's 0 to 5 30t square dt, plus second part is moment coming from the traction force. So it's 0 to 5 15t, this is just the force. We need to multiply this with the distance to calculate the moment. So force multiplied by distance, so it's 15 multiplied by 4 dt, that's the second angular impulse, is equal to m v2 multiplied by d. The car starts from rest, so initial velocity is 0. So now this is 0 plus integral of 30t square is 30 t cube by 3. We need to substitute t equal to 0 to t equal to 5 seconds. Integral of this is 15 multiplied by 4, so it's 60. Integral of 60t is 60t square by 2. We need to substitute t equal to 0 to 2 equal to 5 is equal to mass, which is 150, multiplied by v2 multiplied by distance, which is 4 meters. Okay. When you solve this equation, you will get velocity v2 is equal to 3.33 meters per second. And that's our final answer. Last problem from in-class exercise 4, chapter 15. In fact, this is the last problem from chapter 15. So the 2 kilogram particle A has the velocity shown. So this is the velocity of the particle. Determine its angular momentum HO about point O. Well, I forgot to mention this earlier in the first three problems, but since statics, we always considered anything going counterclockwise as positive for moments. So moment counterclockwise is positive and moment clockwise is negative. So just remember this and always stick to this assumption while you solve the problems. Now this ball has velocity 10 meter per second, its mass is 2 kilogram, and we need to calculate the moment with respect to point O. So there are two ways we can solve this problem. One way is we can actually extend the line of action of this velocity, okay, and find out the perpendicular distance from O, and whatever is this distance, multiply that with 10 meter per second, and that's our answer. And because this moment about this point O is counterclockwise, our final answer should be positive moment. However, it's a little bit tricky to calculate this perpendicular distance. Hence, we'll go for an easy way. And the easy way is you break down the velocity into horizontal and vertical components using the given angle information. So the horizontal component of the velocity is 3 divided by 5 multiplied by 10. And vertical component of the velocity is 4 divided by 5 multiplied by 10. And with each component of the velocity, this is 10 actually. Yeah, with each component of the velocity, we will use the appropriate distance while we calculate the moment. So with horizontal component of the velocity, we will consider this distance while we calculate the moment. And also pay attention to the sign of the moment. The moment of the horizontal component with respect to O is clockwise. So this will go clockwise this way. Hence that will be negative. And moment from the vertical component of the velocity about point O is counterclockwise. So this will result in counterclockwise moment, and that will be positive. And for that we use 4 meters distance. So let's write down the equation for the angular momentum about O, which is sum of moment, horizontal moment x, sorry, horizontal moment, yes, and vertical moment h o y. So we are using scalar approach here. We can actually also do the vector approach and calculate the cross product, but for that we need to calculate the determinant. So let's start with the horizontal component. So it's 3 divided by 5 multiplied by 10, and we put the negative sign here. So this is the velocity multiplied by mass, which is 2 kilogram, and multiplied by the distance, which is 3 meters for horizontal component. Plus sign for vertical component because it's counterclockwise movement. So the velocity component is 4 divided by 5 multiplied by 10. That is the velocity only. Multiply with mass, multiply with distance, which is 4 meters from vertical component. And the result is 28 kilogram meter square per second. And that's our final answer. This terms here, I have used the same simple equation of calculating the momentum, that h0 is mass multiplied by velocity multiplied by distance. It's the same equation. Well, I have just slightly rearranged the terms here. So the first component for me is velocity, second is mass, and the third one is distance. Also velocity, mass, and distance. Positive sign because this is counterclockwise, negative sign because this is clockwise, and resultant answer is positive, so this moment is counterclockwise.